Right now, across thousands of corporate networks, millions of sensitive records are being fed directly into public AI models, ranging from patient medical histories and proprietary source code to primary financial account numbers. Employees do this to accomplish tasks faster, copying and pasting raw, unsecured data into public tools to summarize clinical notes or debug internal code. This creates an unmonitored vulnerability known as shadow AI. Because these prompts are unsecured, proprietary data leaves the company perimeter and becomes part of external training sets, where it can be stored, analyzed, and potentially exposed in a future breach. The standard industry response to these leaks is Cloud Data Loss Prevention, or Cloud DLP. When a user submits a prompt, the packet travels across the open internet to a third-party security server. That server inspects the text, scrubs out the sensitive information, and then forwards the sanitized version to the AI provider. This multi-hub route introduces significant physical network latency. By forcing data through external checkpoints, the system creates the exact type of lag that slows down rapid AI workflows. Furthermore, routing sensitive information through a secondary server creates a new attack surface. Your data is now being processed on infrastructure you don't control, necessitating complex legal agreements and vendor risk assessments. Uploading sensitive information to an external server to protect it from a different external server is a contradiction. It violates the core principle of data minimization by creating an unnecessary data hop. Shifting the security perimeter away from the network and placing it directly down to the user's keyboard solves this. This is the architecture of Zero-Trust Data Sanitization. It ensures data is cleaned locally before a network socket is ever opened. The process begins the moment an employee pastes a record, like a patient history or a financial statement, into their browser. Before the browser transmits the prompt, a local engine intercepts the text inside the browser's volatile RAM, acting as a physical wall against the network. Here, deterministic encryption instantly swaps real identities and social security numbers for generic tokens, like Name1. This allows the AI model to receive the full semantic context for its analysis, while receiving zero actual identity data from the user. Protecting the prompt is only the first half of the loop. You still need the AI's response back on your machine. Because the AI provider only received the generic tokens, its generated answer utilizes those same placeholders. Once that response arrives back inside your browser, the local RAM dictionary translates those tokens back into the original sensitive data. Your context is restored exclusively on your local machine. The airplane mode test provides empirical proof of this architecture. After the page loads, you can disconnect your network and paste in a secure document. Even without an internet connection, the entire scrubbing and reversal process functions perfectly in milliseconds. If the tool can clean and restore data while offline, it is a mathematical certainty that 0 bytes of sensitive information were transmitted to an external server. The security of this ecosystem depends on what happens the moment the task is complete and the user closes the browser tab. Because the process occurred entirely in volatile RAM, the original identifiers and the temporary translation dictionary simply cease to exist. This chart compares standard cloud architectures against local execution. While traditional databases accumulate records over time, the local RAM architecture clears to an empty zero-state log the moment the session ends. There are no server logs, no telemetry, and no centralized database for hackers to target. By ensuring data never rests on unvetted infrastructure, this zero-footprint design satisfies the technical requirements of global privacy regulations like GDPR, HIPAA, and PCI DSS. When data is never physically transmitted to a third-party processor, your compliance status changes. You move from a model of constant vendor auditing to one where the restricted data never legally leaves your control. Managing the risk of generative AI adoption requires solving a specific conflict, providing these models with context while withholding proprietary identifiers. The outdated trust but verify model of hoping vendors secure your data is being replaced by a verify locally standard, enforcing device-level control before data ever crosses the network boundary. Mathematical certainty through local execution is the only architecture that allows an organization to fully utilize AI innovation without compromising enterprise security.